All right, welcome. We're moving on to Module 16, Guide. First, we've got some definitions and answers. The difference between discrete and continuous, remember that we learned this in Module 15. Discrete is countable, and continuous takes on all values in a range. The area in a probability histogram relates to the actual probabilities. The area in each rectangle centered above each value is equal to its corresponding probability. All areas must add up to 1. So if I have some distributions here with each of these areas and values, the probability that corresponds to each rectangle is equal to its own probability, and then the sum should add to one whole. Now, we want to match each of these expressions with the corresponding probability. The first one is done for you. Less than 14, this is the less than symbol. At least 12 means I can be 12 and I can be greater than 12, so I can equal 12 and be greater than 12, which means that E is my answer here, the probability of being greater than or equal to 12. More than 12, I'm going to jump down. More than 12 is A, which does not have that included line underneath. That's the equal to line. So again, between not including 12 and 14 means I don't have the lines. So that probability would be from 12 less than x less than 14. X is greater than 12 and x is less than 14, but it can't include them. And then including the values would be C, where the probability of 12 less than or equal to x less than or equal to 14. Now, from the probability histograms on page 102, they want to know what happens to the bars in the histograms as you increase their width. The bars in the histogram, as you decrease their width, the bars get smaller, so there's more bars, and the curve, like the actual picture, tends to look more like a curve. Remember that the area of a bar in a probability is equal to the probability of its outcome. Regardless of the width, what will be the sum? They always have to add up to a whole or 100%. Now, if we're clicking the Show Curve option, laying on top, what happens to how well the smooth curve matches? As the width decreases, the curve matches better. Once we have a curve that fits our probability histogram very well, what will the area under the curve be? If it matches it exactly, the area under the curve will be one whole, or 100%. Okay, suppose we have a large group of people and record their body temperatures. We then make histograms with the data. What would, let's say we want to measure it with the temperatures to the nearest degree Fahrenheit and the temperatures to the nearest tenth of degree Fahrenheit. Which probability histogram will fit a curve more closely? Well, this is making smaller and smaller pieces, so method 2 is going to match a curve better. We are going to explore probability density curve, and we're going to talk about the empirical rule, which we talked about very briefly a while ago. These have larger widths, smaller widths, and a total area of 1. This is a uniform, or this is a symmetric unimodal area, but our curves could be skewed. They could have different looks to them, but we're going to specifically look at normal distributions with certain standard deviations and means. In each of these pictures, the mean is drawn right down the middle because it's symmetric. But notice that the standard deviation or the distance is different on each of these. They're all unimodal, they're all symmetric, they're all bell-shaped, and they're all centered over their mean, but they're moved based on their how wide they are is their standard deviation. Part C says the inflection point of the curves happens at 1 standard deviation from the mean. The inflection point is where the graph changes from, the first derivative changes from positive to negative, or the curve changes from going concave down to concave up. That's a calculus term, but this is where your graph changes. When you're drawing your graph, you would feel your pencil kind of change of when you hit your point of inflection. It's right about there. Suppose that the finishing times in a race are normally distributed with a mean of 11.5 minutes and have a standard deviation of 0.5 minutes. Let's draw the normal distribution associated, and then we're going to label it. Now, this is a very handy tool that will help us calculate probabilities. These two are equal because being less than or equal to and being less than in a continuous curve is the same thing. So I'm going to try and draw that normal curve where you go up to a peak and down. And each of these marks is a standard deviation. Okay? That means I drop my mean right here, and I do the mean plus 1 standard deviation, the mean plus 2 standard deviations, and the mean plus 3 standard deviations. This problem specifically had a mean of 11.5 and had a standard deviation of a half. Adding a half, I get 12. Adding a half again, I get 12.5. Adding a half again, I get 13. Subtracting, I get 11. Subtracting, I get 10.5. Subtracting, I get 10. We're going to do the same thing for the next problem. Draw your curve. Put your mean in the middle. Standard deviation added to get to the next value. Our average is 44.6. Adding 5.7, I get 50.3. Adding 5.7, I get 56. Adding 5.7, I get 61.7. That is coming from this value here and this value here. Subtracting 5.7, I get 38.9. Subtracting 5.7, I get 33.2. Subtracting 5.7, I get 27.5. I did not shade. Let me shade. This problem says shade the area from 38.9 to 50.3. That would be all of this. Going back up to this previous problem, it said shade the area from 11 to 12. That's here. Okay. Revisiting the empirical rule, we have percentages. Now, the empirical rule says that the area from 1 standard deviation above and 1 standard deviation below the mean is 68%. The areas that I shaded in green on the previous page were equal to 68%. So the probability of being between 11 and 12 was 68%, and the probability of being between 38.9 and 50.3 for those different scenarios was 68%. 2 standard deviations is 95%. That's a typical range of values that we would typically use. And then 3 standard deviations, which is almost the entire curve, is 99.7%. We use this information to make predictions a lot in statistics. Going back to question 9, it says, what is the probability that the randomly chosen student has a height between 38.9 and 50.3? I'm going to label this picture right here just so we can get a general idea. What is the probability that a randomly chosen student has a height between 38.9 and 50.3? Again, that's right here, which is 1 standard deviation. If I was to label each of these, that's 1 standard deviation, 2 standard deviations, 3 standard deviations. And that is 68%. One thing that I find is really helpful is drawing out our distribution and actually cutting the percentages for each slice. And what I mean by that is if I know that 68% is around the mean, if I cut that in half, I have 34% on each side. Because there's 68% total, so there'd be 34 on the left and 34 on the right. Splitting again for the 95%, I would take 95% and cut away the 68% I've already accounted for. If there's 95% here, and I've already handled the 68%, that means that I have 27% left over. Cutting that in half gives me 13.5% here and 13.5% here. The last percentage is 99.7% captured within 3 standard deviations. So 99.7%, but I've already accounted for 95% with my 34, 34, 13.5, 13.5. That leaves me with 4.7%. Split in half is 2.35%. Now, if I've accounted for 99.7%, that leaves me with 0.3% that I haven't accounted for. split in half is 0.15 on either side. Now, if you add all of those up, you're going to get 100% area under the curve. But that helps us when we're trying to determine what the values are. Okay, the next question wants to know a height of more than 56 inches. So 56 is right here to the right. So that would be from right here to the right, which means I'm talking about 2.35% and 0.15%. If you add 2.35% and 0.15%, you get 2.5%. There is a probability of 0.16 that a randomly chosen student will have a height less than how many inches? Less than means that I start over here and I'm going up to what value? Well, I start at 0.15. 0.15 plus 2.35 is 2.5. 2.5 plus 13.5 gives me 16%. So I need to figure out what this value is right here, which is 38.9. And then the tallest 2.5% of students are taller than what height? Again, where is this 2.5 coming from? We have 0.15 plus 2.35 is 2.5. So the tallest 2.5 are going to come from this value and more, which is 56. I know that the empirical rule can be kind of daunting at first, but you definitely want to practice with calculating percents and figuring out what the different probabilities are. We bring that into standardizing with z-scores next.